My name is Danilo Pavo. I am Technical Director, ST and IEEE Fellow in System Research and Application. I work in the EI tool organization. So this is a really great moment for me because I'm so excited to have the opportunity to introduce this tutorial section, which is about the context awareness function path. The tutorial will be held by three colleagues of mine: Lisa Trollo, Artificial Intelligence Strategy for MEMS and Sensor Division; Federico IACCARINO, Product Marketing MEMS and Sensor Division in ST Microelectronics; and last but not least, Carlo PARATA, System Engineer in STM32 Open Development Program, who developed the software pack, which is the subject also of the tutorial. The colleagues will cover the joint usage of the STM32 MCU and in-sensor computing with a machine learning core. Please note the tutorial is not an hands-on, rather contains a number of information on how to get started, so that if you're interested after the tutorial, you will have the opportunity to buy the boards, install the software, and why not run the whole tutorial. You have a unique opportunity to have all the expertise and the colleagues attending. So at the end, there will be available a second room at the end of the tutorial, so that if you have questions or doubts, feel free to take this opportunity. And I leave the floor to Lisa. Thank you.
And hi to everybody. I'm Lisa. And I'm very glad today to guide you in this tutorial where we want to present to all of you the ST Microelectronics distributed deep edge AI solution. Sorry if I'm using the mask, but today we are all in the office and this is the rule when we are in any room of the office. What we want to talk today to all of you. So first of all, we want to define and explain which is the ST strategy for tinyML. Then we will go in a deep description of a context awareness use case. And in particular, you will have all the information about the ecosystem and means software and hardware that you can use to experience this context awareness. Then we will go in a more deep detail about the two algorithms that are implemented in this context awareness, that are the human activity recognition, that is a machine learning algorithm running directly on the smart sensor and inertial module, that is the LSM60SOX. And the second one algorithm that is a neural network, the acoustic scene classification, that is running on an MCU, so the STM32L4. Last but not least, we will show you a very short demo about this context awareness, and we hope you will have all the possibility to experience such AI distributed solution from ST Microelectronics. Let me start from the ST strategy on the tinyML. And what I want first of all to define is the meaning of deep edge AI in ST Microelectronics. So in our company, when we talk about deep edge AI, we think about smart nodes, and in particular nodes where AI can be computed as well as in the microcontroller and also in the smart sensors. So the key point, or let me say the key benefit of such kind of approach in deep edge AI is to have energy saving. So the power consumption of such solution is the best in the market. Then, of course, when we talk about deep edge AI, we have also some other important benefits like the responsiveness of the nodes, the bandwidth limitation, or let me say you can save the bandwidth, and of course you can improve the privacy. But today, where we want to focus and to show you a real practical use case is the deep edge AI, where algorithm runs as well in the smart sensor and in the smart, let me say, microcontroller. Let's go more in details about this, let me say, structure, where you can see on the left side, we have the AI complexity. From the bottom, where we have the sensors, up to the edge gateway and more on the cloud. But let's start from the smart sensors. And here, what ST can offer in the market is a solution of a family of sensors, where inside there is the possibility to run in a machine learning core combined with a finite state machine, some machine learning processing. And in particular, all these algorithms can be implemented using a tool that is named Unico. Then we have also the sensor nodes and points. As we said, the possibility to run AI algorithm at STM32 microcontrollers family. In this case, we have a very well-known tool that is the STM32cube.ai that give possibility to automatically optimize artificial neural networks in this piece of silicon. Then, if you want to have a more complex architecture, we have also solution for edge gateway. So in this case, we talk about STM32 MPU microprocessors. And also in here, we have tools like TensorFlow Lite, XLinux AI, and again, the STM32cube.ai that gives you all the possibility to implement AI algorithm. So now that I have introduced you all the solutions and the products that ST can offer in the market, I leave the stage to Carlo, who will go in a deeply way describing the context awareness function pack, where the AI distributed is the key point of the solution.
Thank you, Lisa. Good afternoon, good morning, everybody. I'm Carlo PARATA by ST Microelectronics, and I'm going to present the new function pack that ST launched on the mass market in the past weeks. This is the context awareness function pack. In this function pack, basically, we used in a combined mode two different AI algorithms. The audio sync classification that runs on the STM32 microcontroller, thanks to the CubeAI library that optimized the code for the embedded device. Then we have also the human activity recognition algorithm that instead runs directly on the smart sensor, the LSM6 DSOX, that is an IMU 6-axis accelerometer plus gyroscope. In this way, when this algorithm runs, we can stop the STM32, and this way we can save the battery of our device. So this is a typical low-power application, very useful for wearable device. For this function pack, we have used as hardware the SensorTile.box, that is an ST eval board available on st.com. This board is sold together with the compact casing, IP54 compliant, with the lithium battery and 8 gigabytes micro SD card as mass memory. And then it has also a BLE module on board, and so it's possible to connect this device to a BLE device like a smartphone. The SensorTile kit is available on our e-store on st.com or through our distributors. It is sold at about $40 per piece. And you can find in the kit also the connector and the adapter to use the SensorTile with the ST-Link box in order to debug and to program the board. What are the sensors that you can find inside the sensor tile.box? We have the LSM6DSOX, the IMU 6-axis accelerometer plus gyroscope with the embedded machine learning core capability. Then we have also two other accelerometer on board, one high performance and the other one low power. Then we have also a magnetometer. And then regarding the environmental sensor, you can find a pressure sensor, an accurate temperature sensor, a humidity sensor, and also an analog wideband microphone. Regarding the processing, the microcontroller is an STM32 L4 Plus MCU, so a low power, high performance family of our STM32 products. Regarding the connectivity, instead, you can find a Bluetooth Low Energy module based on the ST Blue Energy 1 chip. You can find also a battery charger on board. The context awareness is not the only function pack available on st.com for the sensor tile.box. You can find several other software packs for this board. In particular, there is a software pack that show all the basic features of all the components that you can find in the sensor tile.box. We have another function pack for the asset tracking using BLE connectivity. We have another function pack that show all the features of our MEMS sensor that you can find in the sensor tile.box. And then we have also another AI function pack that use the same AI algorithms that you can find in the context awareness function pack. So the audio sync classification and the human activity recognition. But in the AI sensing function pack, it's possible to use these two algorithms only in standalone mode. Instead, in the context awareness function pack, there is the possibility to run the two algorithms together in a combined mode. What is the software components that you can find in the software package? Basically, you will find all the drivers for the microcontroller and the MEMS sensor, together with the middlewares for the Cube AI library, and also for the free RTOS. And then you can find two different applications, one based on BLE and RTOS, and the other one instead that is based on a command line interface application. And so you don't need a smartphone to interface to the board, but just you can connect the board to a PC and then use an upper terminal to interact with the sensor tile.box. So here you can find all the stuff needed to start in terms of hardware. You need, of course, the sensor tile.box and also a micro USB cable for the .box board, and also a mini USB cable for the ST-Link version 2 box. In this way, you can program and debug the software. Regarding the software stuff, all the software is released in source code. You will find the project for 3 different IDEs, IAR, Kyle, and STM32 Cube IDE. But you will find also, if you want, some precompiled binaries that you can use just to start to test the application directly. And for this, you need also an utility like the STM32 ST-Link utility to flash directly the binary file into the sensor tile.box. Then for the BLE application, you need also the ST BLE sensor app for your smartphone that you can find in the Android or iOS marketplace. Or instead, for the command line interface application, you just need an hyperterminal on your PC, so like TerraTerm application. Here you can find the workflow to have the firmware running on your sensor tile.box. Basically, you just need to go to st.com and download the software package. In the software package, you will find all the documentation for the APIs used in the code, the drivers for the microcontrollers and the sensor, the middlewares for the AI library and for FreeRTOS and the Blue Energy connection. And finally, you will find the source code for the two applications, the BLE application and the command line application. Then you just need to use one of the three supported IDEs to compile the code and flash it on the target. Here you can find some snapshot for the ST BLE sensor app for this function pack. As you can see, it's possible to monitor the value of the environmental sensor. Or if you want, you can plot the data of all the sensors on board, like the accelerometer. Then we have some views also to show some hardware features of our accelerometer. And finally, you have a dedicated view for each AI algorithm, the audio sync classification and activity recognition. Then in this specific function pack, you will have also a dedicated view for the combined mode of the two algorithms, where you can run the two algorithms together. In this case, as you can see, for the audio sync classification, we can have three different output states: indoor, outdoor, and in vehicle. Instead, for the human activity recognition, we can load on the LSM6 DSOX two different bytecodes. The first bytecode is needed for the indoor and outdoor use cases. For this bytecode, we can have four different output states for the activity recognition: stationary, walking, jogging, and biking. Instead, we have another bytecode for the in-vehicle use case. In this case, the bytecode foresees three different output states: stationary, walking, and driving. Basically, the logic of this application is that normally only the human activity recognition is running, and the microcontroller is put in stop mode. In this way, we can save the battery of our device. Then when the activity recognition change state, basically it triggers the audio sync classification. And so the algorithm this algorithm can give one of the three possible outputs. According to the outputs, we can decide to change or not change the bytecode to load on the LSM6 DSOX. The audio activity recognition is running in any case periodically with a certain period that can be set in the firmware. At the moment, it is set at 30 seconds. This is the output instead for the command line interface application. Basically, the logic is the same for the BLE sensor. The only difference is that in this firmware we do not use any RTOS. And then, in any case, you can run from the keyboard of our PC through the other terminal the two algorithms, or in a standalone mode or in a combined mode, like for the BLE application. Regarding this function pack, you can find all the documentation on st.com. In particular, for the software part, you can find the data brief and the user manual. And the same for the hardware part, also on the sensortel.box. You can find all the information for this device, so is data brief and the user manual. Okay, I have finished this section. I give the floor to Federico for the next section. Thank you.
Thank you, Carlo. And hi to everyone. I'm Federico. I'm responsible for product marketing for MEMS sensors. And today I'm going to present to you one of our sensors, the latest sensors that came out on the market, which is LSM6 DSOX, which has an embedded machine learning core. And I will show you today how to do some things with this machine learning core built in inside the sensor. So what kind of machine learning we have inside our sensor? We have a supervised machine learning, and the classification that it's used is the decision tree. Why the decision tree? Yeah, it's not that complicated, but it's something that is built in the ASIC of our sensor. This means that this is a real edge AI. Sorry. This is real edge AI, and you can implement a decision tree using nodes, leaves, whatever. And when I uploaded the data, you can decide the classes. So it's something that is completely supervised. I'm sorry. So what we can see here is that based on a decision tree logic, what we need to train our MLC are the sensor data. So since it's a supervised machine learning core, we need to provide this data to our tool. So basically what we do is start a collection campaign of data for using both accelerometer and gyroscope, which are built in our sensor module, or external sensor that can be connected to our sensor via sensor hub. Then we can feed the data to a computational block, which can apply some filtering or digital predefined features to the data that is supplied to our sensor. And then we can implement a decision tree that will be uploaded and will be running completely and solely in our sensor. By checking the results we can see on our sensor, which is the decision made thanks to the decision tree. The data can be then provided to the main processor. This means that the whole machine learning that we are running does not need in any way the main processor to run anything. It just uploads the data inside the decision tree and it's done. Once it's trained, it's done. Let's see here what kind of sensors are available on the market with this particular feature of embedded machine learning. We have LSM6, the SOX, and the SO32X, which are for personal electronics, mainly for wearables, smartphones, all this kind of applications. While LSM6 DSR-X has a really good feature in terms of stability, and that's why we suggest it for applications like navigation, sensor fusion, virtual reality. And then for applications in industrial IoT, we developed two different sensors, which is a sensor module with both accelerometer and gyroscope, which is the ISM32 the HCX, can be used for any kind of application, while IS2 ICLX, which is solely an accelerometer with two axes. So it's basically an inclinometer, and that can be used for structural health monitoring, leveling instruments, and equipment installation and monitoring. Today, what we're going to see is how to implement this, what I said before, this machine learning core, this decision tree inside of our sensor. In this case, we will particularize this application for LSM6 DSO-X. How does it work? We will see it afterwards, but we have basically 5 steps to run. We have to capture the data and basically define the classes. This means that if you acquire a data set, as you may know, you have to classify this data using a name such as, I don't know, static, walking environment, or jogging, running, whatever. After capturing the data and labeling it, basically what we have to do is build the decision tree based on the data that we provided to the decision tree. Once everything is done, we can take this decision tree and embed it in our sensor. And once the sensor is loaded with this new configuration, basically it will process the data by itself, and it will provide as output the decision of which class has been identified in that moment. What we do, what I will show you today is how to use Unico GUI, which is a software available for Windows, Mac, and Linux. How to use Unico GUI to capture the data has been already captured. It's something I cannot do live, unfortunately, but take this data, synthesize a decision tree, and then create a configuration file that we can upload in the sensor to create the decision tree. So this is the time of the demo. I will have to get out of the presentation and get to Unico GUI. I'm sorry, this was not supposed to be shown now. I will show it later on. As you can see now, this is the main window of Unico GUI. I hope you can see it. No, it's not be seen. Okay, I have to stop sharing and share the whole desktop. I'm sorry. Okay. I hope you can see now. Yes, I've been given thumbs up. So basically what we can see here is basically we have to start this software. I don't want to get too much into the details of what we're doing. This software is also supposed to interact with boards. We will unselect the communication with motherboard option, then jump to INAME or immersion modules, and then go to LSM6DSOX. The tutorial that I want to show you today is basically how to implement inside an LSM6DSOX a decision tree which has 3 classes. This decision tree will be, it was acquired, let's say the data for this decision tree was acquired using a bracelet. So this will be for a wrist application for human activity recognition. We will identify 3 classes, which are stationary, walking, and jogging. For more details, I can send you the link to both Unico and GitHub, where you will find a lot of examples like this one to be implemented in LSM6DSOX or other sensors. You will find it in the chat because one of my colleagues will share it to you. In the meanwhile, we can get into the details of the presentation and of the tutorial, of course. So we click on MLC, and here we have the window where we are supposed to load the data that we acquired that we just acquired for implementing the decision tree. These are the training data, obviously. So you can find also this kind of stuff. You can find it on the GitHub. Basically, what you will find are text files where you will find raw data acquired from the accelerometer, the gyroscope, whatever. It depends on the application. In this case, we used only the accelerometer to acquire the data. We will select stationary and set the class label, which this step is the labeling as stationary, and we will load the data. We have to do this for walking class and for jogging class. Once everything is done, we basically imported all the data. We have to use this data to train our decision tree. So we will go to the configuration tab. Once in the configuration tab, we have to select the device, which is LSM6DSOX. Click next. This is the output data rate of the machine learning core. This is, I would say, the rate at which the data is fed to our machine learning core. Usually we select this ODR coherently with the ODR of the sensor. The whole acquisition has been run at 26 Hertz. So the machine learning ODR will be 26 Hertz as well. You will find all of this information in the GitHub. So if you get lost with all these numbers, just follow the GitHub example and you will find all of what you need. We have to select which are the full scale and the output data rate of the sensor that has been used for the acquisition. In this case, it was 4G full scale and 26 Hertz as ODR. The number of decision trees, basically, you can create even more decision trees, but in this case, we just need 1 decision tree with 3 leads. The window length basically is how many data do we wait until we make our decision of the class. I mean, how many data we need to understand if there's a class of static, stationary, or walking. In this case, we suggest to use 52 samples, which are 2 seconds, basically, based on the ODR that was 26 Hertz. So every 2 seconds, our MLC will decide which is the scenario that we are seeing. This gives an option to apply some filtering, like high pass filter, band pass filter. In this case, we don't need it. We can just skip to next. And here, this is something quite tricky, which are the decision of the features. As you know, obviously, this is a trained MLC, so we have to specify which are the features that we want to use to extract the information on the scenario that we want to identify. Obviously, I can help you with this because it's a quite tricky topic. I can help you with a document that the ST produced, which is the design tip for decision tree generation. And my colleague will provide to you a link in the chat. And basically, to provide this, features are basically used to using the data that we have is used to identify which class is which data is referring to which class. So in our case, since we don't have so much time, we can have a look at the data that we acquired. As you can see, stationary, jogging, and walking have quite different patterns. You can see that in stationary, we provided some data where somebody was moving the wrist but was not walking. Then we have some walking data and some jogging data. As you can see, that can be a lot of options of features that can be used to identify which class is which. In this case, since we already ran this example, so we don't have much time to go into the details, we selected as features the mean, so the average of the signal coming from the accelerometer, then the variance, then the peak to peak, the energy, and the zero crossing. I know that making this decision, it can be quite tricky, so that's why I honestly can tell you that our document can give you a lot of hints on how to make this decision. Once everything is done, we can save the IRFF file. I don't know if any one of you is aware of what IRFF file is. Basically, it's a file that's also used with WCA. So I don't know if you are familiar with WCA, but anyway, it's an open file where basically you will find the correlation between the data and the classes. Once we click next and the IRFF file is completed, here we will have to decide which is the numeric output of our MLC, because our MLC just gives us an output, a number. Which number has to be given to detect which any class? So stationary will have the 0 as number, walking will have the 4 as number as identifier, and jogging 8. Now it's time to generate the decision tree. So we can specify using Unico the max number of nodes. So if the lower are the nodes, the easier is to implement the decision tree. Same for the confidence factor. You can find some tips here, but we cannot get into much details, unfortunately, because the time is not that much. We can just basically click using these default settings, click generate. You will find a completely open and easy to read decision tree where all the data is completely clear to everyone. So the last step that we're missing, apart from the meta classifier, which is quite tricky, but basically it's used just to avoid false positives. Let's assume that our decision tree decides that we have walking in a 2 seconds window. If we put 2 here, it means that he has to see for 2 consecutive frame windows the walking, it has to detect for 2 consecutive windows the walking scene to show it to the user. So it's quite is like a counter that you need to activate to detect the scene. It's just to avoid false positives. Once we are done, this is the last step. Basically, what we have done is just creating a decision tree. Now we have to synthesize this decision tree in our sensor, generating this configuration file, which is called UCF. So what we do is just select UCF file, click next And what we have here is a file that can be uploaded in the sensor. And basically, once it's uploaded in the sensor, we'll implement the MLC. So I know we had to rush. Obviously, I'm leaving my presentation to Lisa, which will wrap up the whole presentation. I can tell you, I know that there can be a lot of questions. So if you have questions, just pointing out in the chat. In the meanwhile, thank you for listening.
So I'm just going to present the last section of this presentation, where I will spend some words about the audio sync classification algorithm used in this function pack. So basically, this algorithm is based on the CubeAI library that allows to enhance the sensor technology with AI on an MCU. As you know, you can use as input from a neural network several kinds of sensors like RGB camera, infrared camera, time of flight sensor, audio events or voice, inertial sensor, QR sensor, and so on. Basically, what you just need, you can start to develop your trained neural network model using a standard framework like TensorFlow Lite or PyTorch. And then you can use the STM32 CubeAI library to convert this and optimize this neural network for the MCU. Then it's possible to validate the final neural network that runs on the STM32 or on the target directly or on the PC. The STM32 CubeAI is available with the graphical user interface through a plugin of STM32 CubeMix tool. I don't know if all of you are familiar with the STM32 CubeMix tool. It's a tool provided together with the STM32 microcontrollers in order to select the MCU that you want to use in your application, configure the pins of the MCU, eventually the clock tree, and enable all the peripherals that you need in your application. Then you can add the CubeAI plugin, and this way you can configure, you can import your neural network provided with your preferred framework like TensorFlow Lite or PyTorch, and then you can generate the source code in C program language that is optimized for the STM32 microcontroller. Then you can validate the neural network performances running the validation or on a PC or directly on the target. So basically with the STM32 CubeAI, it's possible to optimize your trained neural network. It's possible also to quantize the neural network in order to reduce the memory occupancy in terms of RAM and flash, and also the latency and the speed of your neural network algorithm. There are several optimizations that are available on the CubeAI library. In particular, you can do a fine-tuning of the weight mapping, also splitting the weights between internal and external memories. And then finally, you can validate the performance of your neural network directly on the target with very small loss in terms of accuracy of your neural network model. Here there is the example that we used for an audio scene classification for the context awareness function pack. As you can see, we started with the trained neural network generated with TensorFlow Lite. On the right, you can find the accuracy of the TensorFlow Lite model in a floating point unit. Then we can quantize the model in an integer 8-bit. And as you can see, as average accuracy, we lose only a few percentage for the accuracy. On the left side, you can find the data set that we used for the training set, validation set, and test set. As you can see, we used 18 hours of audio tracks for the training set, 4 hours for the validation set, and finally 13 hours for the test set. Okay, now we have time for the final demo. I have a short video that shows how this function pack works, together with some snapshot from the smartphone app. So here, as you can see, I used in this demo the sensortile.box with the case and weighing it at the wrist, because all the training of the neural networks was done with this setup. And so in order to have the best performance with the algorithms, it is better to reproduce the same setup. I try to start here the video. As you can see at the beginning, I was in a stationary position, and then I open in the smartphone app the view for the combined mode of the two algorithms. And here you can see the output for the human activity classification. In this case, is obviously stationary. For the audio scene classification, instead, you can see that the output was indoor because I was in a room of the office. Now, as you can see, I started to work. And as you can see in the app, the human activity recognition goes to working state. Instead, the audio scene classification was triggered. And in this way, you can see the output was again indoor, obviously. Okay, that's it.
Thanks a lot to all the colleagues.
Thank you,
so much.
Thank you, guys. We really appreciated the tutorial. I would like to acknowledge again our sponsors. The sponsors are the ones that actually made this, made having a free registration for everybody possible, starting by Newton.ai, who is innovating into the automated tinyML domain, who's also our premier sponsor. Next, we have the executive sponsors. We have ARM, which, as you know, builds from both the software and the hardware foundations for tinyML. We have Edge Impulse, who is advocating strongly, as you all know, for tinyML available to all of the developers. And of course, Qualcomm, who is working as, among other perception, reasoning, and action, and edge and cloud devices in various sectors, such as the Internet of Things, automotive, and mobile applications. And Sentient, who is moving artificial intelligence from the cloud to the edge, which, as you have seen today, it's quite now the trend nowadays. Next, we have our platinum sponsors, Infineon, part of your life, part of tomorrow. We have seen a few of their projects that they work today. We have Reality AI, who is working also in pre-building, in pre-built edge AI sensing modules and tools. Next, we have our gold sponsors. Latent AI is the first one who works on adaptive AI for the intelligent edge. Then we have SenseML, which works on building smart IoT sensor devices from various data. And last but not least, our silver sponsors, EMSA from Israel, Greenwaves, HOTC, Magimop, Quixo, Seed, Studio, and of course, ST Microelectronics. I would like to thank everybody that stuck around until now, and I hope to see everybody tomorrow at 4 o'clock Central European time